Hello. So I want to talk about a few of the key ideas from the balancing act simulation that you did. So first up, in terms of the rules that people come up with, there's two main versions I tend to see with an activity like this. So some people tend to frame their rules in terms of ratios. So if you have two objects, the ratio of force 1 over force 2, where we're talking about the force of gravity that each one exerts on the seesaw, is equal to the opposite ratio of the distances each one is from the center. So the distance object 2 is from the center over the distance object 1 is from the center. Now you could write this a different way, where the product of the force times the distance for one object has to equal the product of the force times the distance of the other object. Either way, those mathematically end up being equivalent, and so they're both useful ways to think about this. Now, the reason I wanted to make sure to talk about the product is that this framing, where we think about the force times the distance, ends up leading us to an important definition. So if I take a look at the formula sheet, if I'm looking in the lower left corner, we're going to end up using this equation right here, where that funny looking T is defined as torque. Now, so when we have that product of the distance times the force, that is defined as the torque. And we'll talk a little bit more about that in a moment. Now, I want to make sure we address this formula. So, first up, you'll notice this formula has two parts. So the middle part looks like this. It has this little perpendicular after the R. This version just means that you use it when the force is perpendicular to whatever object is rotating. So that seesaw, the forces that you were dealing with, they were straight down. The seesaw was straight horizontal, so those forces were perpendicular. Now, when you use this other version, where you have that sine theta, this you're going to use to find torque when the object is, or when the force is at an angle, where that theta is whatever that angle is. So, for example, if instead of just resting bricks on that seesaw, if you had a rope or something similar that you pulled up on one end at an angle, that's when you would use that version of the equation. That's not something we're going to have to do much with. So we have a mathematical definition of torque, but I think it's also important to have a conceptual definition. So we're going to think of torque as something that causes angular acceleration. So just like forces earlier this year caused linear acceleration, torque is going to do the same thing for angular motion. So, for example, if you in that seesaw balancing act simulation put bricks on just one side of the seesaw, that force would cause the seesaw to rotate, so it was applying a torque. Now, just like we could talk about balanced forces earlier this year, at this point we're going to focus on balanced torques. So balanced torques are going to define any situation where the net torque, so the total torque acting on some object, equals 0. And whenever we have a balanced torque, so a net torque of 0, angular acceleration is also going to equal 0. So it'll either keep rotating at a constant rate, or it's going to just stay stationary. And that's essentially a rotation version of Newton's first law. So the last thing I want to do in this video is introduce you to extended free body diagrams, which are going to be a really useful tool for thinking about torque. So earlier this year, we made a lot of use of regular free body diagrams, where we shrunk objects down to a point so that we were only thinking about which forces were acting on them and the size of those forces. Now that we know that where that force is applied matters for thinking about torque, we're going to leave objects as extended things. So as an example, I want to use a screenshot from that balancing act simulation you did. So first thing I'm going to do is go ahead and just label some of these forces, and I'm going to go ahead and draw them where they're applied. So there is a normal force from this 5 kilogram block that is acting on the board at that point of contact between those two. There's also a normal force from this 10 kilogram block, and that's acting at the point where that block makes contact with the board. Now you'll notice I labeled these normal force 1 and normal force 2. That's just a way for me to keep track of these different forces when they're both normal forces. Now, something that's going to be very important and that I'll talk more about in an upcoming video is the pivot point, or the axis of rotation. For now, I'm just going to define that as right in the middle of the board where it's attached to that stand. That's the point that the whole thing rotates around. The reason I need to define that is we're going to measure all of our distances from there. So I'm also going to go ahead and label this on my extended free body diagram. I'm labeling that distance as R1 to remind me that it goes with normal force 1. I'm going to label this distance R2 to remind me that it goes with normal force 2. Now the last two forces I'm going to label aren't ones that came up during the simulation. So the first one is the weight of the board itself, or the force of gravity on the board. Now an assumption I'm going to make, and something that's pretty safe with a lot of things that have these nice even shapes, is that the mass is pretty evenly distributed. So if I sawed off little pieces of this board, as long as they're all the same size, they'd all have the same mass. So that means that the force of gravity acts on the center of mass, which is right in the middle for a nice even shape like this. If the board had one side that was thicker and another side that was thinner, that would move the center of mass. But when it's nice and uniform, center of mass is usually in the middle. Now, if I think about this for a moment in terms of balanced forces, right now I have 3 forces acting downward. But this board is at rest, which means that the forces on it must be balanced. So what's balancing all these downward forces is a third normal force from the stand that I'm going to go ahead and add to my extended free body diagram. So there we have it. This is an example of an extended free body diagram. And in the next video, I'll talk a little bit about how we can use these to set up the math.